Hello, let's go through the features of a three-phase source. Before going to the details, here is an example of what you can do. Here is a model of a small three-phase power grid. We have 4 transmission lines with breakers on each side, a couple of resistive loads and 3 three-phase sources. On the top right is an infinite bus and the 2 other sources are generators with transient and subtransient characteristics. Here are the 4 transmission lines. And down there we have 2 breakers which will have to clear a short circuit which will be initiated by the switch here. Let's run the simulator and adjust the power supplied by the 2 generators. Once everything is set properly, I push the transient recorder button. This initiates a preset switching sequence. All of this is recorded, as you can see now. You can now zoom in into interesting details. More of the transient recorder in another video about transient recorder. Let's now have a look at the 3-phase source. It basically works the same way as a single-phase source, but with some important differences, however. Right click and you can choose on the menu either to flip or rotate the source. For doing so, please watch the dot which is placed on the R phase of the source. Whenever you connect several 3-phase sources, the dotted phases have always to be connected, otherwise you mess up the phase sequence. So you see that if the second source would be connected like this, with the dot on the bottom, it would not be correct, therefore we have to flip the source. You can flip it either on the menu or directly on the input form on this box here. Now everything is correct, the 2 dots meet each other and I can connect the sources correctly. I can now tick the generator box and I can also add some subtransient, transient and stationary reactances to the source. I can use it either separate or in combination. When I use the combination, I have a completely integrated generator model, including transient, subtransient and stationary reactances. Let's now run the model. The red arrow is the terminal voltage of the generator. Let's now increase the torque of the generator to 100%, so we achieve frequency stability. Again, the red arrow is the terminal voltage of the generator. The black arrow corresponds to 1 pu or nominal pole wheel voltage. The blue arrow is the adjusted pole wheel voltage enabling the terminal voltage at given load. Here is the slider adjusting this inner pole wheel voltage. The angle between the arrows is the generator rotor angle. It corresponds to the red circle segment on the source model. The indicator underneath the source is the generator terminal voltage in per unit of nominal. The red, blue and black arrows are not shown in the simulator, it is just for demonstration. By the way, I can also switch off this view meter if I want. You see it's gone now, it's not there anymore. I can also run the generator without inner transient reactors. In this case it is only a voltage source but with controllable torque. In this case the terminal voltage is equal to the pole wheel voltage. Or alternatively I can run the source including an internal transient reactance, but this time without torque control. So you can watch the interplay with other connected sources when you slider the angle of the source. Here is an example of a generator on the left side feeding power to an infinite bus over 2 200 km line segments. They are compensated by reactors. You can see the effect of switching on and off the reactors. So far the generator doesn't feed power yet to the system. Let's now feed power by increasing the generator torque. You can observe how the rotor angle increases as well as the angle between the voltage of the sending and the receiving end of the lines. The oscillation in the power trace you may have seen at the beginning of the torque increase is due to the temporary DC components, mainly through the reactors. By the way, there is this three-phase source without star ground, which can be used, for example, in cases you would like to simulate the effect of harmonics on a network. This is a very simple one now, so let's just have a resistive load, three-phase ohmic load, and let's see how this looks like. So we would have a 10% harmonic source, voltage source on the source side, 500 Hertz. You can add more of them, of course, if you want, in series. And I would have a relatively high load impedance. And let's check the impact now in this running the simulation. Here it is. You can see this is the total harmonics at the load side. Here comes a teaser. How can you build a simulation of a short circuit a little bit remote of 4 smaller generators, for example hydro generators, feeding a system? Play with the system, start small until you get a good feeling on how it works, and then you can gradually improve your expertise with www.ecsb.ch. I wish you all the best.